In a previous video, I showed you a Hamiltonian path on our dodecahedron. To review, a Hamiltonian circuit visits each vertex of a graph exactly once, and forms a closed loop. Here's the Hamiltonian circuit model from that video. You can actually use this Hamiltonian circuit for another purpose, to create a three-coloring of the dodecahedron's edges. An edge coloring is one where the edges of a graph are colored so that no two adjacent edges share the same color. Obviously, the more colors you have, the easier it is to satisfy this condition. But with only 3 colors, the problem can be quite challenging. In fact, it's not immediately obvious that it's even possible to 3-color the dodecahedron. At first, this problem may seem unrelated to the Hamiltonian circuit, but I'll try to unlock some of the intuition for you. Let's return to the plane graph for a moment, with a Hamiltonian circuit drawn onto it. Notice that each vertex is connected to 3 edges. Since the Hamiltonian circuit visits every vertex, we know that every vertex is connected to 2 edges on the circuit, and 1 edge which is not. If we simply change every other edge on the circuit to a different color, we generate the 3-coloring we're looking for. Since we alternate colors along the circuit, we know that every vertex must have 1 of each of the 3 colors connected to it. The circuit never crosses itself, so we don't have to worry about the colors sneakily coming together somewhere else in the graph. Now all we need to do is use the plane graph to help us assemble the 3D model. In the same way that there's only one Hamiltonian circuit on the dodecahedron if we ignore reflections and rotations, this is a unique 3-coloring of the dodecahedron. This can be really helpful when planning out a modular origami project. A similar strategy can be used for other shapes. In fact, for any given graph, if D is the largest number of edges connected to a single vertex, what we call the maximum vertex degree of a graph, the minimum number of colors needed to create an edge coloring of that graph is either D or D plus 1. For example, the dodecahedron's maximum vertex degree is 3, and it turns out that it can be colored using just 3 colors. For an arbitrary graph, however, determining whether D or D plus 1 colors are needed is no small task. We might look at some examples in some future videos. But for now, if you enjoyed what you saw, be sure to like, comment, and subscribe, and I'll see you next time for more foldable math.